Hello, and welcome to this video on rotational motion. Specifically today we're going to be talking about torque and static equilibriums. When we talked previously about equilibrium, when the net force on an object is zero, we specifically focused on the net force in the x and y direction. But when we start talking about rotational motion and the chance for things to pivot, we have to go a little farther. Here we have a picture of a toy mobile, the kind that you hang from cribs for babies to look at and stare at. And in order for this to stay in the air, not float around and not pivot, we do need to keep the sum of all forces in the x direction to be zero. We need the sum of all forces in the y direction to be zero. The x direction is fairly easy. There's nothing really moving left or right. The only forces we have are acting up and down. In this case, gravity, tension, and repeat. In addition to factoring all the tensions, we also have to factor the mass of the sticks themselves. Typically, when we talk about the mass of the stick, we treat it as all the mass being at the center of mass and it pulling down from there, like so. Now, in order for this to balance out, all of these forces have to be balanced. We could focus on an individual beam, or we could focus on the whole picture. But in the x and y direction, all these forces need to be balanced, and so it doesn't start accelerating up or down, so it doesn't fall into the curb or fly into the air. But we also have to talk about the torque, because if the torque isn't balanced, these will start rotating one way or the other. And that rotational motion will also be a problem. For something truly to be at equilibrium, to be static, not only does your sum of all forces in the x direction, the sum of all forces in the y direction both have to be zero, but the sum of all your torques also has to be zero. Now, we're not going to do this problem right here. It's a little needlessly complicated, but we'll take a look at a simpler one. Three masses are attached to a uniform meter stick as shown below. The mass of the meter stick is 150 grams, 0.15 kilograms. M1 has a mass of 50 grams. M2 has a mass of 75 grams. If I want this entire pendulum, this entire mass to balance, what should mass 3's mass be? Now, this is fairly easy if we rotate from here. Finding how all the torques balance is straightforward. And even in this case, we don't need to care about the normal force or the force gravity. I have three torques on the left side. I have the force of gravity acting down from this point. I have mass 1 pulling down here and mass 2 pulling down here. On the right side, I have mass 3 making an unknown motion. But I can still write my sum of all torques. The torque of the stick, this torque of the mass 1 and mass 2 are all in blue because they're on the left side and they're what I can find and calculate. The torque of M3, my unknown, goes on the right. You'll notice that I am including the mass of the meter stick this time. In the previous video, I left it out because I was pivoting about the center of the seesaw. The mass was right at the point where the balance was. In this case, that's not true, so we have to go a little further. The nice thing about this, though, is I'm looking for it to balance, be level. My acceleration, or my net torque, should be zero. That'll make things a lot easier. From there, all I need to do is write in all my torques. A simplifying assumption we're making once again is that all these forces are acting at 90 degrees, which makes sense. These are all right angles, but that's just to get us eased in. So from here, let's just plug in some values. The radius to the first mass from here to here is 70 centimeters or 0.7 meters. The force is going to be M, which is 0.05 kilograms times 9.8. Or G. I'm going to leave it as G for now. You'll see why in a second. Plus 0.4 times the 0.075 of M2, again, times G. These being M times G, which would be my force gravity exerted by these strings. And I can continue on. You'll notice that I left g in everything, but g's a common term. It can factor out because there's a 0 over here. We can cancel out. Second, you'll notice that I put a negative sign in for the green term, the m3. This is because in each of these cases, if I look at my right-hand rule, I get my thumb pointing out of the screen or out of the page. I get a positive torque. Each of these forces here on the left are going to cause this to rotate in the positive direction, counterclockwise direction. Whereas this one's going to cause it to rotate in the clockwise direction. Again, using my right-hand rule, I get my thumb pointing into the screen or the negative direction. From here, I just need to solve. You can do that. Go ahead, give it a try. Check back after you're done. If you've done the math, you should get 316.6 repeating grams. You'll notice that I multiplied all my terms, added them together, and then did my algebra through, giving my answer of 0.316 kilograms. But the more useful answer is 316.6 grams. That's it. That's all we needed to do. Set up, solve. The only real hard part here is picking a point where we could ignore unknowns. And once again, don't know, don't care. We don't know the normal force. We put our axis of rotation somewhere where we don't need to care about it. Here, at the top. Consider this problem instead. The 65-kilogram woman is doing it in a horizontal push-up position. What are the forces acting on her hands and feet? We're going to make the simplifying assumption that everything's acting perpendicular, all the signs are 90. How do we solve this? Well, the way we kind of are conditioned to solve this, we know that there's a normal force here. The force gravity is pulling down at the center of mass. And there's a normal force here. These three forces will have to give me a torque of 0. So in this case, I'll label these 1 and 2. The torque from the first normal force plus the torque from the gravity plus the torque from the second normal force all have to add up to 0. Now, if I pick up axis of rotation, picking one where it cancels out, let's say this one over here, I will find fairly quickly that I can simplify this down. The first one has an R of 0 times Fn1. Force gravity is at 0.5 times mg, and then torque 2, 1.5 Fn. I do need to put in some signs here. This going from this point here, gravity goes down, which means I will get a negative torque. And this normal force here goes up, which will give me a positive torque. And this needs to add up to 0. I can then go through and solve 0.5 times 65 times 9.8 equals 1.5 Fn. Simplify, solve. I get Fn equals 212.33 repeating newtons. Now, once I'm here, I can do the same trick. I can flip it around, and instead of going from this point, go from this point, and I can do the same trick. The only difference being in this case that my force gravity would be a positive torque and my normal force one would be a negative torque. But because the person is standing still, the sum of their forces in the y direction also has to be 0. So my normal forces added together minus my force gravity has to be 0. Either way I do this, I should get the same answer. Give it a try. Check back. As we can see, sum of forces y and the torques both give me the same answer. The normal force on the hands has to be 424.66, repeating, or 424 and 2/3 newtons. This simplification, this multiplication here, is one of the many tricks we'll run into. And in fact, many times you don't know multiple forces and you need to find them using a system of equations. You can set up the sum of forces y or the sum of forces x and your torques. Typically it will be y because it's just how brains work more conveniently, and we tend to hang things that rotate. Anyways, thanks for watching. Have a good one.